Wait, 1, 2, 3.
Nothing happened.
It worked the first time.
It's a matter of timing a lot of times. So try it again. Let her hold the balloon and the finger.
You do it. Use your color to both. All right, go both.
Yeah, one person should do both. So balloon comes near, finger allows electrons to escape. Both go away.
It works.
And the electroscope gets a charge. Now, what kind of charge does the electroscope develop? Alright, so
Wait a second. How does it work? So,
now think through how that's working.
our tracks will be positive.
And I'll just film this piece of paper for a minute because if you... Okay. Okay. So now you've had some time to think this through. So let's talk about what happened. All right, everyone attention. So part 3, number 1, charging by induction. Rub the balloon on your head, bring the balloon near the loop, but touch the loop with your finger. Then move the finger and the balloon away at the same time. What happened?
The foil stayed apart.
Okay, the foils moved apart and stayed apart. So number 2, your observations hopefully were foils moved apart and stayed apart. So, charging by induction, even though your finger is touching, the thing you're using to charge the electroscope, the balloon, never touches the electroscope. Key point there. Where do the electrons go in number 3? Right. So that big negatively charged balloon is repelling all the electrons out of the loop and foil. And they have a pathway to escape. They don't just have to hide in the bottom of the foil. They can get out through your finger. So when you pull away your finger and the balloon at the same moment, are there the right number of electrons on the loop and foil? No. Fewer or too many? Fewer. Electrons have escaped. They've run away through your finger, and there are fewer electrons in the loop and foil than there ought to be. So what charge is there going to be?
Positive.
A positive charge. Negative electrons have run away, so the net charge is positive. You have more protons in your nuclei than you do electrons orbiting them. So number 4, you're going to have a positive charge. And number 5, why did the foil stay apart after you pulled your finger and balloon away?
Because unlike charges repel.
Like charges repel.
Like charges repel.
Right. So both foils had the same charge. Both foils were positively charged. They had too few electrons. They're both positively charged. So if both foils are positively charged, they repel each other. All right. So then... well, I'll give you a second. The foils repelled each other because both foils were positively charged, and 2 positives repel. My hair's probably wrecked. Number 5, that should be that. Number 6 says, touch the loop with your finger again and record your observation. What happens? Well, hopefully you already did it. But they should have already been separated. So then if you touch, what happens? I think I touched yours. Ooh, theirs did it. What happened? They went back together. So why did that happen? When the foils were apart, you touched the loop, they go back together. Why?
Because the electrons from your finger went back to the...
Exactly. They got their electrons back out of your finger. So once you've touched it, what charge should your electroscope have?
No charge.
No charge, neutral. So the key point, which you could write again, but I've apparently written here for you, when you charge by induction, you use a charged object, in this case a balloon which is negative, to give the electroscope the opposite charge. Our negative balloon made our electroscope positively charged because it drove the electrons out, leaving it a positive charge. Okay.
Number 8, though.
Number 8. When you charge an electroscope by induction, we gave the foils what kind of charge?
Positive.
Positive charge by repelling their electrons with what kind of balloon? Negative. So conduction gives the same charge as the object you're using to charge. Induction gives the opposite charge of the object you're using to charge. Okay? So that's the overriding key point that I want you to take away. And we're going to go over study guide now. And at the end of that lab sheet, there's Module 12 Quest. Module 12 Quest. You guys can do Module 12 Quest at home this week. We're going to go over it in class. Make your best attempt at it. Because you definitely will learn more from your mistakes than you learn from your successes. So it's fine, get them wrong, get them right, but try them, okay? Now we're going to do the study guide. All right. So grab your study guides and let's talk. First key point, all of these definitions are on the test. All of them. There's a lot of them. I have A through G, and they're all on the test.
A through G?
A through G.
There's 6.
4, 5, oh, I have 7. Man, I must have the old one again.
7.
Learn them all. Okay. Number 2, we'll start with Jessie. Number 2 says this. For the following situations, put it away, all balloons, throw them over there or something. For the following situations, draw the force exerted by the solid object with the solid arrow and the force exerted by the dashed object with the dashed arrow. So, Jessie, we've got...
Describe it.
Yeah, describe it.
Draw on the board. It's too much long.
So, would that negative thing attract or repel that positive thing? Does a negative charge attract a positive or repel a positive? Okay, so a negative charge is going to attract a positive charge, unlike charges attract each other. So the positive will exert what kind of force on the negative exert what kind of force on the positive. So use your fingers to show, like, make your hands into the two charges.
I'm so lost.
Meredith?
Yes.
I don't know how to...
Duchesne?
Yes.
Do you have your problem in front of you?
I do have the problem.
Okay. What will those two charges do?
So the negative and positive will attract.
Right. So their little arrows will point toward each other. Okay. Let's go back to Jessie here. So B has 2 negative charges. Make your hands into 2 negative charges.
I don't know how to do that.
Just hold your
What do
hands
you want me to do?
like this.
Okay. There they are. Are they going to move toward each other or apart from each other? Apart. Okay. So you want to draw arrows making them look like they go apart. Is that all you guys have, or do you have? Okay. I have a note that there's some other question somewhere. Okay. So A should attract, B should repel. That's the key point. All right. So Meredith. 3 says this. If the force between this, oh, we didn't talk about magnets yet. Okay, so if the force between the south pole of a magnet and the north pole of another magnet is measured, if the distance between the poles is increased by a factor of 3, how does the new force compare to the old one? Is it attractive or repulsive? Okay, so this is just like the problems we did with gravity. Exactly the same. And so I'll aim. All right, so remember that equation that we used.
F equals...
Oh, there's my marker. So what was the equation Meredith, that we used for gravity? It was the...
Mass 1, mass 2.
Okay. So remember we figured out what the factor of change was for the masses, the factor of change squared for the distance, and we just multiplied those together to find out how much the force changed. With the electromagnetic force, if you're dealing with electricity or magnetism, is very similar.
I wish Wild would explain it like that, because the way he explained it in the book was weird. The way he said to do the math problem.
Really?
He didn't do F equals anything.
Oh. Let me read the problem. Where did I put it? The force between the magnets. Okay. Well, let's do it the same way we always do it, right? If the distance increases by a factor of 3, how will the new force compare to the old one? So we're not changing, and the mass isn't what changes. Like the amount of charge or the amount of power the magnet has would be here, which is why he's ignoring that, because you guys don't know how to figure that out. But if we have magnets and then we move them further apart, will the amount of force between them increase or decrease?
Decrease.
Okay, so there it is. You stay with me here. Okay, so if we have magnets, we move them apart, the amount of force decreases. What in the world is going on? All right, so it says this, that the distance is increased by a factor of 3. And it even gives you the factor. You don't even have, it's not like it goes from 3 to 9 centimeters or something. So the factor of change is 3. Is increased by a factor of 3. Okay? 3. So then we use essentially the same equation. We don't change anything up here, but we change the distance squared. We put in 3 and then we square it. So what's 3 squared, Meredith?
3 squared
9. So the force will increase by 9 times or decrease by 9 times? Decrease by 9 times. Because when it's a fraction like that, that means, and what does it even call it a force? Yeah, the force will decrease by 9 times.
So is there like a repulsive or whatever
Right.
the other one was?
So we're
I was
going to ask
confused.
that next. So Meredith, the force between the South Pole and the North Pole. So with magnets, does the North Pole attract a North Pole or a South Pole?
We haven't gone over that yet.
It's the same
West
as
pole.
Electrons. Opposites attract. Right. So the North Pole and the South Pole are going to attract. Okay. So it's an attractive force that decreases by 9 times when you move them apart. And you guys know that when magnets are further apart, they don't pull on each other as hard. When you get them closer and closer together, they do. And I'll bring some magnets next week so you can see that happen. I mean, I have strong enough magnets that when they get close enough, they just jump together.
Put your hand in between.
So,
Yeah, they'll actually go between your hands.
yeah,
It's really
it
cool.
hurts too.
It does hurt.
I hope I can find my really strong ones.
They make a really loud noise when they go together.
My physics class breaks magnets every year because they're really brittle, the really strong ones.
That's so cool.
But they do find out, every year they discover something that I've never seen happen before when I just let them play. It's really fun. My physical science class has a bad reputation for totally destroying my stuff.
Really? Can you find us some meteorites that are magnetic?
No. You guys have been very good. I don't just hand out my magnets for throwing around there until you're in physics, but we'll play a little bit. But you have to.
Can we bring some of our own? Like those ones that you throw in the air and then they go together?
I have a set of those that you can play with. Let's do 4. Duchesne, you do that with me. 2 charged particles are 10 centimeters apart, and then you measure the force. Then you double the charge on object 1, and you leave object 2 alone, and then you reduce the distance. So, what do you think doubling the charge will do? Increase or decrease the force?
Increase.
And what do you think decreasing the distance will do?
Increase.
Increase. So both of these things are going to increase the force. So instead of mass and mass up here in the numerator, like gravity had, we're going to have the factor of change of the 2 charges. Physicists call that Q, but that's confusing. So here's my eraser. Q, the charge, amount of charge is Q.
What's weird though, they don't
I'll
give
call
you
it
like
C for you
the
guys.
how much mass 1 and mass 2 have. They just say like mass 1 is then double.
Well, because then all you have to do is multiply it by 2.
Oh, okay. That makes so much
So-
sense. I needed another number, but I guess you don't need one.
All right, so for Duchesne, charge 1, charge 2, and distance. So charge 1, what's the factor of change for me?
2,
2, because the charge is doubled. Charge 2,
1.
it's a factor of 1, it doesn't change. And then the distance, what happens to it?
It's multiplied by 1/2 because
It goes from 10 to what? To 5.
it's a half.
So Okay, so now we just plug in exactly the same way we did the math in the last module. So force is going to be factor of change of 2 times factor of change of 1 divided by factor of change of 1/2 squared, because that's the distance.
Which is 1/4.
Right.
So
So 2 over 1/4.
which is actually 8.
Okay, so that's 8, and the way you do that, 2 divided by 1/4 is really 2 times the inverse of that, 4 over 1, which is 8. So, and when you end up with a number that's not a fraction, that's a whole number, that means 8 times greater. So the force increases by 8 times. And does it ask anything about that force?
No.
No, okay. So just 8 times greater. So you do it exactly the same way as problems from the last module. You just find factor of change, factor of change, factor of change, and then plug it into that exact same equation. And I don't know how he said to do it. If his way works for you, that's totally fine. If my way works, totally fine.
His way is confusing.
I found it to be
He
confusing.
didn't use an equation. He just explains it, which is fine. but
Yes.
It's nice to have both.
Yes, I agree. Every possible way you can think about a problem is good. All right. So Joshua, I need to point this at you guys. What causes the electromagnetic force, Joshua?
An exchange of particles of photons.
Photons, not protons. Definitely photons. So photons are packets of light. Exchange of photons causes the electromagnetic force. So, Patrick, why can't we see, if photons are light, why don't we see glowing when magnetism is happening or when the electrons jump to the loop in the electroscope experiment? Why don't we see it? Photons are light,
Large
right?
particles do not glow because the protons they unite are not visible to you and me.
Right. So visible light has a wavelength of 400 to 700 nanometers, but there are light of greater and less wavelengths, and we can't see those, but they still exist. I mean, bees can see some of them that we can't, and other animals can see some that we can't. And of course, we can use machines to sense the colors or the wavelengths of photons that we can't see with our eyes. They're still there, even though we can't see them. I know that sounds obvious, but you know. Joseph, number 6 says, no, 7. Did you do 7, or is that where we stopped? We went to 12.
No, that was for the study. I mean, for the summer. No,
Summer is 7.
Oh, that's okay, though. Don't worry. Just finish it all for next week. So Joseph, 7 says, if you were to use a positively charged rod to charge by induction, what charge would the object get?
The object will get a negative charge.
Right. And how did you know?
Because when you charge an object by induction, it always gets the opposite charge the object needs to charge.
Perfect. I've had physics classes that don't get that as quickly, so good job, you guys. That's great. Ryan, if you use a positively charged rod to charge by conduction, what charge will it get?
Positive.
And how do you know? He just said it. Okay, so induction gives you the opposite charge of the thing you're using. Conduction gives you the same charge as the thing you're using. That's just the definition. Chris, number 9 says an electrical circuit, and we'll talk more about circuits next week too. An electrical circuit uses a large voltage and a small current. Is the energy of each electron high or low?
It is high.
High.
Yes.
High energy. Are there many electrons flowing through the circuit or few?
There are few.
Few. So large voltage tells us large energy, small current tells us few electrons. Is this circuit dangerous?
Yes.
Yes. Number 1 rule, always assume all circuits are dangerous. Number 2 rule, if both of those things are very low, you might be okay. Any circuit I give you is going to be completely safe to touch. If you use like those 1.5 volt batteries, you're always going to be safe. You can't hurt yourself hardly, even if you use 2 of them.
But don't play with
Yeah. No, 9 volts hurt. One of my physics classes told me to touch it to my tongue, and that really hurts. Don't ever do it. I did it. It hurts.
Why? Tongue on a cold lamp post. You don't do that.
That's terrible.
Unless you're
I'm
triple dog
gullible.
daring.
You're the teacher.
I
No,
wouldn't do it. I wouldn't double dog for long. Wouldn't do it.
It doesn't hurt
Why
that
didn't they just
much.
pour water on it? If they would have
Exactly.
they would have poured water, it would have melted it.
So
Instead of
true.
pulling it,
Yeah.
instead of just pulling it out, like how.
Okay, it's your question, Lily. Number 10, under what conditions is an electrical circuit reasonably
So
safe?
it's gonna start on like where it's gonna move. You mean like the red line? Is that what you're saying?
No, I'm on number 10. When is a circuit safe?
Oh, when the voltage and current are low.
Both have to be low. So, Bethany, draw a conventional current flow. So tell me about conventional current first, Bethany.
basically the current would go from the starting point all the way to the end point.
Positive.
And just keep looping, positive, negative, just looping.
Okay.
Over and over.
So, I'm going to, Grace, will you aim for me? Not Grace, Jenna, will you aim for me? Sorry. I'm going to call you Anna next week, just to cover all my bases. Aiming for now.
okay.
All right, so here's the deal about conventional current. We know now that electrons are negatively charged particles, right? So when you have a battery, electrons are going to flow from where they're charged up, right, negative charge, to around to the positive end, because negative electrons are attracted to the positive end of the battery, right? But they had a functional circuit working before they knew that. So somebody, Ben Franklin, just had to say, current's flowing this way, and he just guessed wrong. So he said that current flows from positive to negative, which kind of makes sense, right? He didn't know that the negative part of the atom is the part that can get broken off and fly around. So he said, well, let's make current go from positive to negative. Now we know it goes the other way. So conventional current is always drawn the wrong direction. Nobody wants to change all the hundreds of years of electrical plans that were written before we figured it all out. So you always draw conventional current from the positive end of the battery around to the negative end, but we know the truth now that electrons always flow from negative to positive because they are negative. So I'm going to draw the battery here, and then Bethany, you come up and draw the current. So when you draw a circuit, you're going to draw a battery, and the battery has a big line and a little line. And the big line is the positive end, and the little line is the negative end. And like if you draw a circuit that we make in class, if I give you two batteries, you can always just draw it like that, right? But still, this is going to be the positive end, and this is going to be the negative end, okay? So then you draw a circuit that goes all the way from one end to the other. If there's a break in the circuit, current doesn't flow, right? So you have to have a completely connected circuit, a closed circuit for current to work. So Bethany, you come up. Can you get up here? Is there a path? We have a closed circuit. We have an open closed circuit. She can make it. Okay. So see if you can get the blue to work. And draw conventional current the wrong way.
Miss Matthias,
Yes.
the positive side is smaller than the negative side.
Seriously?
No.
Positive side's supposed to
Yeah.
be the big side, isn't it?
Positive's
but
big
it's
side.
wrong.
Positive's big side.
This should be the big one.
Yeah,
This
that's
is the
supposed to
big
be
one.
bigger.
Yeah, that's a little one.
And the negative's a little.
There we go. It's not moving.
Are we good now?
Did she get the bell back?
Yeah, that's the right way. We get it.
Okay, so conventional current goes from positive to negative. Am I still wrong?
No.
Okay, that's great. But truth, okay, she's really trying hard here drawing this one. She's really trying hard to draw from positive to negative. That's how conventional current should be drawn. But in truth, we know it will be the other way. And I guess we'll start again next week. So all you need to do is finish Module 12. Make sure you're ready to turn in last week's lab. Stay here if you haven't done that lab, and you can stay. And do the quest
Oh, you
and
want
do
the
your
lab
best.
now?
Only if you're completely done and feel good about it. You can turn it in next week if not.
Are we gonna get our lab from this last week, next week?
Did I not turn stuff back today? I did.
No, we did. Last week's lab
Was the lab pretty slow? If you turned it in, I'll give it back.
What were you talking about? The horses and kind of spaces. There's nothing stopping it from going straight.
No, because it was stopped in you had two different forces. One force was keeping it going in a circle, the other force
Two
wanted to go
forces will
straight.
be at motion.
Just look in the book, it explains it better.
I get it, I just couldn't think about it.
Well, how you have to think about how to write it down. You know what it means in your head.
Yeah, I just can't think of how to word it. It's like, one force will be moving in this direction. I was like, what is
So
she saying?
I just wish we could think to one another, and then they would understand your point of view immediately, and then you wouldn't be like struggling with words. Because words are so inconvenient when you're trying to get across a point that doesn't make sense to other people. Convenient in the fact that we can have to communicate with each other, like some animals.
So it's nice.
Wolves can, and a lot of animals can communicate, but not like humans can.
Yeah, that's probably good.
As far as we can tell, wolves can communicate fear, happiness, all that. Hello. Yes, random person just got here.
I left mine here for
It's still recording.
Or take it with you or pop it and get it in the trash can or anything at all.
Oh, I have pins. How convenient.
Loud noise. Is anybody staying for the rotational motion lab? Okay.
I can do it after.
Okay. Do you want a thing?
The sheet? I got a sheet.
You got a sheet. Do you want a thing to twirl around?
Sure.
Okay. It'll make it a lot easier.
I did see your